Okay, so we are going to do an example of signal classification. Here are classification categories here that are presented in class. We'll go through each one. They're not in any particular order necessarily. Here's our example equation. So we've got y of t is equal to sine t plus 1 quantity squared. We'll start with analog versus discrete. And we can almost do this by inspection. So here we have a continuous t variable. There's no restrictions that we see in this on what t can be, which means this is not sampled. Right, it's not sampled, it is continuous. So it's definitely not a discrete signal. Let's check our y value. So y value is similarly not quantized, so it's not quantized. It's not forced into specific buckets of values. It can vary anywhere that sine this quantity can vary. There's no modifications on this equation or in the sampling itself that drives the y value into quantized values. So this is not quantized. It is also continuous. And so we have an analog signal. B, our frequency composition. Okay, let's go ahead and expand this out. Okay, so we've got three terms. What are the frequencies on these? So here we have frequency of 1. Here we have a frequency of 1. And here we have a frequency of, well, it's constant. So we have, these are the same frequency. So these are the same frequency. Which means we have a single frequency signal here. All right, C. C is symmetry. So symmetry, we could have an odd signal or an even signal. Let's write our function out here again. It's not obvious just looking at this whether it is odd or even, and in fact, we will decompose it into its even components and its odd components. Signals can be deconstructed into even and odd components if they are not themselves obviously even or odd on face value. So let's go ahead and do that. So y even is 1/2 of yt plus y minus t. So what do we get there? We get 1/2 sine squared t plus 2 sine t plus 1 plus sine squared minus t plus 2 sine minus t plus 1. And this will end up equaling minus 2 sine t because sine is odd. And so an odd function is a reminder. Y of minus, well, an even function. So equals minus y of t. That's an odd function. Okay, so this will end up being negative, which will cancel out here, and we will be left with 1/2 of 2 sine squared t plus 2, which gives us sine squared t plus 1. So these are the components up here that are even. So that's our even components of our function. And y odd, we can do y odd also, y odd. 1/2 y t minus y minus t, right? Okay, so this is going to be 1/2 sine squared t plus 2 sine t plus 1 minus quantity sine squared minus t minus 2 or plus 2 sine minus t plus 1. Distribute this minus and cancel out the parts that match. So this will cancel, that'll cancel because sine squared is even. This will cancel and this will cancel because they're even. And we will be left with these two terms. We'll be left with 1/2 4 sine t, and that is 2 sine t. So our odd component. That's our odd component, and this is an even component, and this is an even component. So we have found y odd and y even for this particular signal. Let's check what we're doing next. Continuity. So we'll do D for continuity. So for continuity, we want no jumps, no infinite slopes. That's what we're looking for there. It's not discontinuous. There's no holes. So we have our function y of t equals sine t plus 1 squared. So let's take the derivative of that. And that is 2 sine t plus 1 cosine t. All right, there's nothing on the bottom, so we don't have any holes. Cosine t, sine t, and 1 are all continuous functions. There's no jumps or gaps, so we see no jumps, gaps, holes, no infinite slopes. So this is continuous. Next we have periodicity. So here's E. Periodicity. Is it periodic? Does it repeat? So we've got y of t equals sine squared t plus 2 sine t plus 1. This is constant. So yeah, it's the same for all values. That's got a period. Infinite, it's continuously the same. So any value we add, any increment of t, we get the same value there. This is also periodic because sine is periodic at the plus k pi to t. This is also periodic, right? So sine t has the same period as sine, so plus k pi for our period here. So we see that all of the components of this are periodic, and that means that the signal overall is periodic. Next, we have scale composition. So scale composition is kind of a flexible term. This means this is kind of to describe, can we see all of the frequencies on the same graph? There's not a hard and fast rule for what determines what becomes multi-scale or multi-resolution. What we're trying to identify is this single or multi. I tend to use a rule of thumb that if the ratio of magnitudes of the signal components is less than 10, so if this magnitude ratio is less than 10, then I would call it probably single resolution or single scale. So our components here, we've got t, we'll just write it again, sine squared t plus 1 or plus 2 sine t plus 1. So here we've got a magnitude. Here we've got a magnitude. Here we've got a magnitude of 1. Here we've got a magnitude of 2. Here we've got a magnitude of 1. But this isn't changing, so that really doesn't matter. So these magnitudes are the ratio of the maximum magnitude, so max mag over the minimum mag. Here is 2. This is less than 10, so I would call this single resolution or single scale. G is randomness. So we've got two options here. It can be deterministic, or stochastic. And we can see from our equation up here, this is an analytical equation, right? I can predict the value for any value t. I plug in any value t, and I get a known singular response, y. So this is deterministic. We've got stationarity. Stationarity, is it growing systematically over time or not? Is it bounded? So we've got y, we've lost the equation, we'll rewrite it. Sine squared t plus 2 sine t plus 1. Okay, so this term is bounded between 0 and 1. This term is bounded between -2 and 2. This term is bounded between 1 and 1. All right, so if I add all these up, I get total bounds of this thing being between 0 and 4. All right, so this is bounded. It's stationary. Right, the output values are bounded within some finite range. We get a stationary signal. Next, we have regularity. We've got regularity here. And for regularity, did we already compute the derivative? Yeah, so we already computed the derivative for the continuity to see if there are holes, jumps, gaps, and it is continuously differentiable. And so we actually get regularity out of that too. So it is not singular. That's the main thing we're looking for with this one is it singular? Is it, like a delta function or a step function, some impulse? It is not one of those. And so we get a regular signal. So we get regular there. I skipped causality on our list, so we'll go back to causality. So H. Is it causal or non-causal? Well, let's check. So we've got y of t sine squared t plus 2 sine t plus 1. Does it have values at minus t? Yes. Are they non-zero? Yes. Does it have values at plus t? Yes. Are they non-zero? Yes. Okay, so this is non-causal, right? Y has values both in the minus t and plus t domains, and neither are zero for all time minus t or for all time plus t, so it is non-causal. Support. What is the support of this function? So what values of t, so what values of t is y non-zero? And we have three terms. Looks like it is always for any value of t. So t minus infinity to infinity, y has values that are non-zero, which means this is non-compact support. Next we have causality, regularity, support, integrability. H I J K. That's K. K. Integrability. So we want to check absolute integral. Absolute. Is it absolutely integrable? And we want to check square integrability. So those are the two things we're going to check here. So we'll find out if this is absolutely integrable. So absolutely integrable of our equation. So we take the integral from minus infinity to infinity y of t dt. So that is the integral of, we write our equation here. We had sine squared t plus 2 sine t plus 1 t. All right, so we'll take this in parts. So we'll do the integral of sine squared t dt, the integral of 2 sine t, and the integral of 1. All right, so this is t. We evaluate that from minus infinity to infinity, which is infinity minus minus infinity. So we get infinity. That's a problem. Not absolutely integrable, right? So right there we already know. Integral of sine is known as minus, so we get minus 2 cosine theta, or t. I'm using t's, not thetas. T minus infinity to infinity. Now this could be minus 2, so sometimes this is 0, and sometimes this is minus 2, right? So that's the bounds of this here. But the limit of this does not exist at infinity or minus infinity because it continues to oscillate forever. So this doesn't have a limit. So also not absolutely integrable because this doesn't have a limit here. And sine squared, you end up using the half angle formula identity to convert this into 1 minus cosine 2t over 2 dt, and then integrating the sections of this. So we end up with 1/2 times, we've got a t there that comes out of this. And then we have minus sine 2t over 2. And we evaluate this from minus infinity to infinity. And again, we have an infinity there, and then something that does not have a limit. At infinity, it continues to oscillate forever. So again, we do not have convergence to a finite number here. So this equation is not absolutely integrable. How about a square? Square integrable. So we will. There are equations that are square integrable but not absolutely integrable, and vice versa. So it just depends on if their limits exist, if they become finite numbers, but when they're squared or not. So things that, so for example, 1 over t squared does have does converge. 1 over t to the first power does not converge, right? So that's a case of where we have a square integrable function, but not an absolutely integrable function. Okay, so square integral, we've got minus infinity to infinity, absolute value of y t squared dt. And so we've got our base equation of sine squared t plus 2 sine t plus 1, and this whole quantity squared dt. So we're going to get a bunch of terms here. So what do those bunch of terms end up being? We end up with and I'm going to drop the absolute sign for now just because of how many terms there are. Sine fourth t plus 4 sine cubed t plus 6 sine squared t plus 4 sine t plus 1 to the 4th. Okay. dt. All right, and then again, we're going to integrate each of these individually. And I think you should be able to tell from the analysis above, we're going to get pretty similar results that we did in the absolute integral, right? So here we have something that does go to infinity. Here we have something that does not exist, doesn't have a limit. Here again we have does not exist, does not have a limit. Sine cubed. I assume would be the same. Definitely sine to the fourth does not exist. And we're taking absolute values of this, so we're going to end up with all positive values. So again, where this is going to continue to oscillate forever. So this is also not square integrable. All right, next we have, is it an energy type? Versus power, or it could be neither, right? So it doesn't have to be one of these, it could be neither. So K was integrability. L, there we go. So energy signals need to be square integrable. So we kind of already determined that this cannot be an energy signal from this result here. So we know it's not an energy signal. So is it a power signal? So for a power signal, we're going to divide this by 2 periods, and we're just going to integrate it over 2 periods. So from minus t to t of the energy equation itself. So that's the square, the absolute value of the function. Which, if you chuck these numbers into a solver, you end up with 35 pi over 4 for our power. So this is our power here. This is a power signal, right? This is a finite value. So we have a finite value here, and that makes it a power signal. We have infinite energy, because here we got that infinite energy there. And I think that concludes all of the classification categories we were looking at. Yep, that is all of our categorizations.